this. We know that exists. We don't know if this. We don't know this this t bar, but it's we don't care. Still, we know that that the norm of p prime of t bar is equal to 10, which is also equal to yeah, x prime of t bar square root of 1 plus 9 t bar to the power 4. Okay, now this gives us, if you do the component-wise thing, actually gives us that this is equal to 2, right? And we can actually use this information to solve the equation at the previous line, because we know something. So so these two together here, and now I have to change page. I'll do this, and then I go back here. So those two things together gives that 10 is equal to is t bar square root of 1 plus 9 divided by 16, because I'm using that fact. So this is x prime t bar, and then you do you get 5 divided by 4. So this implies that x prime of t bar is equal to 8. So now we have to figure out which is the sign of this. I think it says something. Yes. So actually, the exercise says something a little bit more about, because now we have to figure out if we have to take plus 8 or minus 8. But we had an information given from the text. So we knew that the text said that the particle was moving in this direction towards the right. So it means that the tangent is this one and points in this direction. Maybe I can change color. So the red thing here is p prime. And you can actually see that, well, probably in both cases. No, actually, no. You can actually see that the y component, well, maybe this is ugly. Okay. One moment. So the x component of this vector, this red vector p prime, the x component is positive. So because it points, it's very hard to. It points in the positive direction. So we have a positive component, so it means that we can take actually from this picture, we understand from the picture, we understand that x prime of t bar is equal to 8 and not minus 8. Okay, well, we're done now. So conclusion, p prime of t bar is equal to 8 comma minus 3 times 8 divided by we had x of t squared, so we get 4 here. This is equal to 8 comma minus 6, and this concludes the exercise. Let's let in the people. Okay. Yeah, so all right, so okay, so you actually, I'm actually going to I mean, unless, okay, let me see, there is a question. Could you show the last page? Yes, I can. So unless there are specific questions, or unless there is, unless you want to see exercise 17, I'm going to skip it. I'll leave that for you, and I go to the section 3 of chapter 11, in which we are asked to parameterize curves in the space. And yeah, that's what I'm going to do now. Okay, I'll go ahead. Okay, so let's see, 11.3. 11.3, we have exercise 11.3.5. Okay, so we have this problem. We have two cylinders. So the cylinders z equal to x squared and z equal to 4y squared intersect in two curves. One of which passes through the point through the point 2, -1, 4. So we want to find a parameterization of that curve using y equal to t as parameter. So in this case, the parameter suggestion is given. So they suggest to use y equal to t as a parameter. In general, maybe it's not given. It's a little bit harder. You have to figure out. But this is actually, I mean, this is quite clear. So first of all, you see that from z equal to x squared, you get that z must be equal to, x must be equal to plus or minus the square root of z. So okay, so the intersection between the two cylinders is nothing but just solving these equations. And what do we get? We get plus or minus z comma y comma 4y squared, if you want, or yeah, actually, yes, you know that, I mean, this will also be equal to plus or minus 2 times the modulus of y, and 4y squared. And since well, actually, I don't need the plus or minus here. Just take the modulus here, and so if t is equal to y, then a parameterization is p of t be equal to 2 times modulus of t and for t squared. Okay, so now, I mean, here I have to make a choice. Since I have this modulus, I don't like it. So I want my point to pass through the point. So I want P to pass through the point 2, -1, 4. So, for example, for t equal to 1, the last component, it would be okay, but then we have a positive. So, for instance, so I can say that P of t, this parameterization here, t, for t negative, is okay. Now this is a choice. You can play around with the signs and with the modulus to get something else. But you see that if t is equal to -1, I get that P of -1 is equal to 2 -1, 4, which is the condition. And also, again, you can take is okay. Also notice that P3 of t is equal to P1 of t squared, and P3 of t is equal to 4 times P2 of t squared, which is exactly what we started from. So we had two cylinders, we intersected them, and then we have this. This parameterization is fine. But x can be negative. Well, the point is that yes, it can, but when you take the square root, you generate essentially two branches of this curve. So it's like when you have a parabola here, which is described by y equal to x squared. When you take the square root, you have that x is going to be equal to plus or minus y, so square rooted. So one branch is x equal to plus the square root of y, and the other branch is equal to minus the square root. So when you take the square root, you identify two branches, and we're doing essentially the same, I think, because I mean, I think that's what this text says. It says the two cylinder intersect in two curves. So what it means is that we have two branches. I selected one. I selected the correct one. So that's what happens here. Okay. Let's see the number 6. Very easy. So the plane x plus y plus z equal to 1 intersects the cylinder z equal to x squared, and then we want to parameterize the intersection. Parameterize the intersection. So here you can select, so choose x equal to t as a parameter. So we get, so from the equation of the plane, you get that y is equal to 1 minus t minus z right, which is going to be equal to 1 minus t minus z, which is equal to x squared, so t squared. So yeah, the conclusion is that the parameterization is p of t equal to t 1 minus t squared and t squared. And this is the parameterization of the intersection. Okay. And the number 7 similarly. So you have this kind of problems. So we have a cylinder x squared plus y squared equal to 9 intersecting a plane. Intersecting plane. Intersecting actually the plane. Z equal to y plus x. Okay, in this case, maybe it's not that easy to come up with a parameter because the choice is not, maybe it's not immediate. You can actually, well, one possibility would be to a choice, a possibility. A possibility is to set x equal to 3 cosine t and y equal to 3 sine t. You see that yeah, so you see that this this selection fulfills the equation of the cylinder, and then from this you can just say that z is equal to 3 times cosine t plus sine t. So turns out that our parameterization is 3 times cosine t sine t and cosine t plus sine t. Yes, so this is what we have. Okay, let's go a little bit ahead. I'm going to solve the number 15 and then we take a break because it's almost 11. So exercise number 15. Yes, so this is I mean, these exercises that we are going to do, they're essentially about solving solving integrals. So you have seen in the class that you have actually a formula to express the length of a curve. So if you have some curve in the plane or in the space, I don't know, some curve that starts here and then you would like to compute the length of this curve. This curve will be given by some parameterization yeah, so the idea, of course, when you have a smooth object is, I mean, the idea behind the formula that you are going to use is that you always try to break this curve up in small segments. That's the principle here. You do small segments and then you refine this construction and then to the limit process, this will be, you can prove that this approximation using segments is actually converging, or this sequence of approximations, it's actually converging to a number, and that number will be the length of the curve. Okay, so this is just a very, very intuitive level. We are not interested in the mathematics now behind. We are just interested in doing computations, and computations are might be rather tricky, but that's because there are integrals to be solved, and the integrals might be tricky to be solved. Okay, so let's see. We want to compute the length of the curve. Now I lost the, where is it? Right. Okay, so we want to express the length. So express the length of the curve r of t a t squared bt c logarithm of t for t that belongs to 1 comma t, capital letter, as definite integral. Evaluate the integral if b squared is equal to 4ac. Okay, so so first of all we need to compute the derivative of this thing. We have 2at, and then we have b, and then we have c divided by t, so that's the derivative, right? And we need the modulus of r prime of t, or the norm actually, which is the square root of the sum of the squares. So we get 4a squared t squared plus b squared plus c squared divided by t squared. This is what we get. Right. So now, of course, so the length of this curve, length of r between 1 and t is given by the following integral. Is the integral between 1 and t of this object here that we just computed, and this is 1 to t of the square root of 4a squared t squared plus b squared plus c squared divided by t squared in dt. So this is the number that I mean, probably this is impossible to solve by primitive techniques. So indeed, the exercise wants us to investigate the case. So we investigate the case b squared equal to 4ac. But I see that now is 11. So let's have a break for 15 minutes and then catch up, and we finish this computation here. Yeah, if you have questions, you can just type there. I go to the toilet and read them afterwards. Hey, Oscar. I'm reading your question in the chat. Yeah, I don't mind. I will answer to your question, but I will pick this thing up also the next time because it's a very important topic. Yes, so you are correct in what you say, but instead of talking about intersection between a function and a line, I would talk more about the restriction of f along some curve, and specifically you're mentioning two straight lines. So, but this is what you say is correct. In general, to prove that a limit does not exist, it is enough to prove that the limit of a function along two different curves, no matter if they are straight lines, parabolas, cubic, or other kind of things, they are different. So if you manage to do that, you proved that the limit does not exist. And this is essentially an extension. If you remember in the first variable analysis, you had that a limit exists if and only if it exists along all the sequences, right? So and the principle is the same here. Instead of having sequences, you have curves, but you can just pick a sequence along that curve, and then you get that your limit does not exist. So I hope this is a little bit more clear. But I mean, I will talk about this as soon as we get to the computation of limits. So don't worry about that. I'll be back in 5 minutes. I'll get a cup of coffee and then we start. We go back to our problem. Okay, so let's go ahead. So we were about to investigate, we were about to compute explicitly this integral. So in a specific case, so in the case in which b squared is equal to 4 times ac. Okay, so what happens in that case? You see that, so in this case, we have that the norm of r prime of t is equal to the square root of 4a squared t squared plus 4ac plus c squared divided by t squared. And now this is something that we can simplify a little bit because this is a square. So we get 2at plus c divided by t squared. And this is just the modulus of 2 times at plus c divided by t. Okay, so the length is now the integral between 1 and t, capital letter, of the modulus of 2at plus c divided by t. And now, I mean, just for the sake of the calculations, I want to assume that a and c are positive, otherwise you have to distinguish all the cases, so I get rid of this modulus. So for the sake of simplicity, for the sake of calculation, calculations, assume a positive and c positive. It's not otherwise it's just more boring to distinguish all the cases, so we don't want to do that now. It's not really interesting. So this we get rid of this modulus because t is also positive, so this number is always positive, and then we get this. And now this is easy to compute. So this is going to be equal to, okay, maybe I should change page. It's going to be equal to at squared between t and 1 plus c logarithm of t between t and 1. So this is a times t squared minus 1 plus c times the logarithm of t. And that's the length of this curve. So you see a very complicated object, but still it's possible to compute lengths. So sometimes it's not. Like, yeah. Okay, so let's see the number 17. So I anticipate that, I mean, this kind of problems are essentially one variable analysis problems, because I mean, once you have a curve and you want to compute a length, you just need to take derivatives, and this you know how to do that, and then you have to compute integrals, and this you know how to do that. But integrals are not always they are not always easy to compute, like in the case that we are seeing now. So we might need some patience or some. Okay, so now we have this this curve here that is defined by t cosine of t, comma t sine of t, and then t, and then t belongs to 0 to pi. Okay, we want to compute the length. Compute the length of r for t that belongs to 0 to pi. So r prime of t is equal to cosine of t minus t sine t, sine t plus t cosine t, and then 1. And then the length of r is equal to the integral between 0 and 2 pi of the norm of this guy in dt. So what is this? Okay, maybe I go this 2 pi. It's the square root of, too long, square root. Okay, so we do all the squares, so we get cosine squared of t plus t squared sine squared of t minus 2 times sin t cosine t, and then we get plus sine squared of t plus t squared cosine squared of t plus 2 times t cosine t sine t, and then we have plus 1, and everything is in dt. So now you can see that there are some cancellations here. So this guy together with this guy gives 1. And then you have that this guy together with this guy gives t squared. And now you have that this guy cancel with this guy. So it simplifies quite a lot. Not enough though, but quite a lot, yes. So this is going to be equal to the integral between 0 and 2 pi of, we have the square root of 1 plus t squared plus 1 in dt. So that's integral between 0 and 2 pi of 2 plus t squared in dt. So now we have this then integral that, okay, so if we had minus t squared, so if we add the square root of 2 minus t squared, that would be easy to solve because you know how to solve it doing a change of variables. You just set t equal to sine or cosine, and then you can actually simplify it quite easily. In this case, unfortunately, we cannot. So now I'm going to do this. So this is going to take quite some time to be computed. I'm going to do the computations carefully for just once, because we will meet this integral other times in the future, and I will not solve that integral anymore in the future because I'm doing that now. So you have two choices here. So one choice that would be quite simple to do. It's a change of variables, so you can use those so-called hyperbolic functions. So two choices to solve, two choices to solve this integral. So choice number one, use hyperbolic functions. What are hyperbolic functions? So hyperbolic cosine of t or of x and hyperbolic sine of x are defined as e to the power of x plus e to the power of minus x divided by 2 and e to the power of x minus e to the power of minus x divided by 2. So these are the hyperbolic functions. If you do the change of if you do a little bit, maybe this can be left as an exercise. You can see for yourself that they hyperbolic cosine and hyperbolic sine, they fulfill some sort of trigonometry. Well, maybe I can do the computation. So let's see. So if you take the hyperbolic cosine and you just square it, what do you get? You get e to the power of 2x plus e to the power of minus 2x, and then you have plus 2 divided by 2 divided by 4, right? And if you do hyperbolic sine, you get e to the power of 2x plus e to the power of minus 2x, and then you have minus 2 divided by 4. And this means that if you do cosine of hyperbolic cosine squared minus hyperbolic sine squared, you get 1, right? And I would like you to notice that while cosine of x squared plus sine x squared is equal to 1. So there is this symmetry between, that's one reason why they are called hyperbolic cosine and sine. That's only one. Received a message. No, something else. Okay, so, and then you can actually prove that if you differentiate the cosine of x, you get the sine, the hyperbolic cosine of x, you get the hyperbolic sine, and vice versa. So they are very nice functions. And if you do the substitution, t equal to hyperbolic sine, in that integral you can get a nice thing. So maybe this can be left for you as an exercise. The past years I've seen that students were a bit confused about these hyperbolic functions. I don't know why. So I decided to just leave this thing as an exercise. So how do you do that? You just to conclude the computation of the integral, compute cos h prime and sine h prime and do the substitution. T equal to, it should be t equal to something like, I don't know, in our case would be the square root of 2 sine, yeah, something like that. So you get rid of the 2 and then you get, yes. Okay, so this is left for you as an exercise. You can do that. What I'm going to do is a more classical but much longer solution using instead another change of variables. Okay, so first of all, I'm going to solve the indefinite integral. So just forget about the endpoints for a moment. So I consider this thing in dt. So, okay, so let me call it I. So I is equal to, and now here I do the change of variables, t equal to the square root of 2 tangent of u, which gives me 2 times the integral of 1 divided by cosine to the power of 3 of u in du, because you get some cosine squared from the dt. Now if I okay, so now I can do some integration by parts. So this is going to be 2 times, and now I have 1 divided by cosine of u times the integral, no, times sine of u divided by cosine of u, which is nothing but tangent of u. And then I have, yeah, I need more space. Okay, I want to do some surgery here. Let's see if I manage to use this function. I want to move, no shit. Oh, okay, nice. Okay, so now I'll do, this. Okay, so now I have minus the integral of sine of u divided by cosine of u times sine of u divided by cosine squared of u in du. This is by parts, and that's because I am considering, so this cosine here, I see this cosine as 1 divided by cosine of u times 1 divided by cosine squared of u. So 1 is the derivative of the tangent, and then you differentiate the other thing, you get what I got here. Yes. Okay, so I'm just doing one empty step. So I have 2 times sine of u divided by cosine squared of u minus integral of sine squared of u divided by cosine to the power of 3 of u in du. Okay, now I do another almost empty step. So I do sine of u cosine squared of u minus, and then I write the sine squared as 1 minus cosine squared divided by cosine to the power of 3u in du. What does it say above sin of u? Tangent. So this whole quotient is tangent of u, of course. Yep. Sorry for my handwriting. Okay. All right. So now what do we get here? We get again. We get 2 times sin of u divided by cos squared of u, and then we have minus integral of 1, another empty step, but I prefer to do all the steps for once. And then we have 1 divided by cosine of u du. Now, first of all, you see that we started from this green thing. We started from the integral of 1 divided by cosine to the power of 3. And then here we have again the integral of 1 divided by cosine to the power of 3 with a minus. So we can actually dump that thing on the left-hand side to simplify a little bit the expression. So if you just put together the 2 green things, what we actually get is that 4 times the integral of 1 divided by cosine to the power of 3 of u in du is equal to 2 times of sine u divided by cosine to the power of 2u plus 2 times integral of 1 divided by cosine of u in du. Okay. And this is equal to 2 times sine of u cosine this plus 2 times. Now this is a logarithm. We can compute, this is something that you find, for example, I think at the end of the book there is a table of integrals. Right, so I'll just maybe omit this step. If it's not clear, just try to convince yourself why this is true. So now this it actually has a primitive. Maybe this is a little exercise for you. So this purple one, exercise for you. Okay, now we have to go back to the previous variable. We did a change of variable that was t equal to the square root of 2 times the tangent of u, and that means that u is equal to the arctangent of t divided by the square root of 2. So we have to go back. So first of all, we can see that this is actually 2 times the tangent of u, because we have sine divided by cos squared, and we just take one cosine, and then we have cosine of u plus 2 times logarithm of tangent of u plus 1 divided by cosine of u. So do we get this table of integrals on the exam? I don't know, honestly. But I think that the purpose of the exam, of this exam, is not to test your ability in computing integrals. or rather to test your ability on something else. So either yes, I mean, if there are some particularly hard integral, it will probably be given, like I mean, this primitive is blah blah blah, or you can just have a table of integrals, something like that. This I don't know this detail, but in general, the integrals that you can find in the exam, the integrals that you can find in the exams are not like this one, so it should be much easier to compute. Okay, so now what's the problem here? We have to figure out how to get rid of this damn 1 divided by cosine u. Okay, so first of all, you can notice that that 1 minus 1 divided by cosine squared of u is equal to cosine squared of u minus cosine squared of u minus sine squared of u divided by cosine squared of u. This go away, and then we get minus tangent squared of u. Yes. Just give me 1 second. Yeah, I'm confused now, sorry. What do we want it to do? Right, so I wanted to do this. So this, of course, means that 1 plus tangent squared of u is equal to 1 divided by cosine squared of u, which implies that 1 divided by cosine of u, maybe in modulus, is equal to the square root of 1 plus tangent of this, right? Yeah. So I guess that in our case, we don't need to bother with the modulus, because 1 divided by cos u is always positive, at least between, well, actually, no. It's not always positive. Yeah. How do I get rid of this? Just give me 1 second. Well, yeah, okay, so I guess that we might need a little bit of careful, but yeah, I mean, the point is that here what I wanted to write is that 1 divided by the cosine of u, which is equal to 1 divided by the cosine of the arctangent of t divided by the square root of 2. Now we have seen that cosine of u is equal to something that involves the tangent squared. So you actually get 1 plus t squared divided by 2, which is actually a nice identity. Okay, there is this thing of the modulus, so you might need to take plus or minus, but now I don't see that, and I don't want to waste more time on this. So this is now something that I want to just like some side thing, and now I get that this the last equality that we have. So using the identity in the red box, in star, we get star is equal to square root of 2 times t divided by the square root of 2 times 1 plus the square root of 1 plus t squared divided by 2, which is 1 divided by cosine whatever in the arctangent, and then we have plus 2 times the logarithm, and then we have a modulus of t divided by the square root of 2 plus or minus. This has to be checked. I don't want to do that now, so I leave that to you. There might be some signs problems here. So we have t times 1 plus t squared divided by 2 plus 2 logarithm of t divided by square root of 2 plus 1 plus t squared divided by 2 plus a constant, of course, because we were doing. So I guess, and I hope that now this is over. So, well, in conclusion, so we wanted to compute the integral of this function. And now we have computed a primitive or an antiderivative, so you just use that information. You get that the result is pi times the square root of 2 plus 4 pi squared plus the logarithm of the square root of 2 pi plus the square root of pi squared plus 1. So that's the solution to this exercise. So the computation should be fine. Just maybe you might want to go through and check if all the signs are okay. Yeah, so yes. Okay, so as I said, this is an art integral, and exercise 19, actually, the integral to be computed is I'm actually probably harder, so I don't really want to go through that one too. So, so you see that here the difficulty is about computing integrals. Of course, with these hyperbolic functions, it would have been much easier, but it's good to see two solutions. These more just the tools that you have from analysis in one variable. So I skip the 19. I go to something slightly easier. Well, actually, we have 15 minutes. Let's see. Maybe okay. Let me do the number 20, and then I'll see what to do. Okay, so I'll do the number 20. Okay, so we have the curve with the parameterization t to the power of 3 and t to the power of 2. And we want to compute the length, of R for t belonging to -1, 2. So the procedure is the same. You compute the first derivative, you get 3 this, you get 2 this, then you compute the norm of R prime, and then you get 9t to the power of 4 plus 4t to the power of 2. So you actually see that yeah, so this is what we get. So we get a modulus of t times the square root of 9t squared plus 4. Okay, so the length of R is equal to the integral between 0, actually no, between -1 and 2 of the modulus of t square root of this plus 4 in dt. So I split the integral in two because now we have this modulus. So I'll take a minus here, minus t, because yeah, when t is negative, I put a minus in dt, and then I have plus the integral between 0 and 2 of t times 9t squared plus 4t. Okay, so what do we get here? So this is going to be equal to, you can directly compute primitive here. You have a minus 2 divided by 3 times 18. Well, I could have simplified that, times 9t to the power of 2 plus 4, everything to the power of 3 divided by 2. Because if you take the derivative, yeah, you see that you get that thing. And then this has to be computed between 0 and minus 1. And then we have plus the same thing, but computed. Well, yeah. Nope. We have 2 divided by 3 times 18. 9t to the power of 2 plus 4 to the power of 3 halves between 2 and 0. So this is going to be equal to, well, you do the math and you get 1 divided by 27 minus 16 plus 13 to the power of 3 halves plus 40 to the power of 3 halves. Yes, so this is rather easy, but yeah, this number is sucks. So yeah. Okay. I think there is. Okay, we have still 10 minutes. Instead of doing some complicated integrals, I think that there was. Let me just check. I think there was. Could you please? I don't want to. I don't have the updated schedule. Could you please tell me if exercise 3 from sheet number 1 is among the exercises that we were supposed to solve in today's session? Compute domains of some functions for the next lecture. Okay. Okay, then yeah. Let me see. Just fast. I'll just check the schedule myself and see, because I don't remember. Analysis in one variable. Course plan. Yeah, you're right. That's going to be the next class. Yes. Yeah. Okay. So instead of doing complicated integrals, I think I can maybe go back to, since in the last seminar we didn't. Yes. So you're right. So we have also, there is also exercise 19 for today, but I'm not gonna do that because it's too long. It takes too much time. So you can maybe if we have some spare time we can do that another time. But it's not very important. Instead, we can maybe I can maybe go back to the previous seminar classes and see if we have some. There were a couple of exercises that I didn't solve about like sketching things and boundaries and sets. So I can do a couple of them and then we can just conclude. So I'll draw a line here and let's do some exercise 1 from the sheet number 1. Okay, so this is a task in drawing and sketching sets or boundaries. So sketch the boundary of some sets, and then we have, okay, so the A set is called M, and M is x squared plus y squared strictly less than 1, and this is a subset of R2, and this is very easy. You recognize what it is. So this is a circle of radius 1, center 0. So you have this, and then the boundary of this object here, that is usually called with this partial M, the boundary is going to be the set of the points where we have equality, right? The boundary does not need to belong to the set itself, right? In this case, it doesn't. So the boundary is actually the circle. While, sorry, I used the I abused of the language. I said that M was a circle. Is not a circle. M is a disk. So what's in the interior here is M. So this black thing is M, and then we have red is boundary of M. So this is the boundary. The B case, for instance, we have that M is equal to x squared greater strictly than y, and x squared plus y squared greater or equal than 1. So we have this object, which is maybe a little bit more complicated. Let's see. Let's do a picture. So first of all, we have some circle now. Well, we recognize the equation of something related to a circle, but there is an inequality now. So inequality means that we are taking things outside, right? So all this black thing here is what's outside the circle. Yes, and then we have another object, which is y strictly less than x squared, which is this guy here, at least, yes. And then we need to understand, maybe I should use different colors here because it gets more complicated. Okay, so I'll use green for this parabola. Yes, so we want to see which side we have to pick because we have inequality. So for instance, you see that point 0 minus 1 fulfills the equation, the relation x squared greater than y. So from this, we understand that the part of the plane that we are interested in is this one here. Okay. Included the, okay, yes. Okay, so essentially, if we use just yeah, I mean, if we consider the two inequalities together, the set that we are considering is this red one here. Notice that I am outside the circle, so the red thing portion is M. It's a little bit messy, this. So what I wanted to draw is the black is one thing, the green is another thing, and the red is, but maybe I just messed with the, yeah, well, I don't know exactly how to do. But now we have to compute, well, first of all, we have to compute the boundary. The boundary is going to be given by this, and then we go down here. Maybe I can use, so the red thing here is the boundary of this set, right? This is boundary of M, the red thing. And if you want to compute it explicitly, we need to intersect these two things. So the intersection between x squared plus y squared equal to 1 and x squared equal to y is given by x squared plus y, sorry, y squared plus y equal to 1. And then you solve, and then you get y is equal to 1 plus or minus the square root of 5 divided by 2, which means that we get two intersection points. Of coordinates, the square root of minus why there is a minus. Okay, wait a second. Okay, well, so the two intersection points have coordinate. I don't know why I did write. With a minus. Yes. Wait a second, I have done a mistake here. This is minus 1 plus or minus the square root of 5 divided by 2. Okay. Okay. So now, if you take, we have to take the plus sign, because the minus sign doesn't give us the intersection. So we have minus 1 plus square root of 5 divided by 2, and then we have the positive root here, and the other one will be the negative root. Minus plus square root of 5 divided by 2. So these 2 points are essentially this one here and this one here. And given that, now we can actually compute, write down explicitly the boundary. So the boundary of M is going to be literally the set of the points maybe I can write this as a union. Let's see. On the parabola, we want x to be greater or equal than this value here in modulus, because we are on, and but then we have to take a union again. Let me use this cutter here. Why can't I move it? Okay. Yes. And then union together with the set of the points on the circle, such that x is strictly less in modulus than that number that I wrote there, minus 1 plus the square root of 5 divided by 2. Yes, so this is the boundary, which is the red thing here. I hope that's clear. I think I messed a little bit with the picture, but you can try to redo the exercise yourself and look at my solution and then convince yourself. Okay, so it's 12 o'clock. I'm going to stop here. stay here for a few minutes. If you have questions, you can ask them. Otherwise, have a nice weekend, and see you on Tuesday. Or, well, I don't see you, but yes. I'm gonna put this this file in the canvas like I did last time, maybe this afternoon, so you can go through the things that we did again. Yeah, I don't know if I want to record the classes. Well, I can think about recording and putting them on Canvas. I don't know how to do that. Because I mean, since I'm like essentially talking to myself, there might be possibility that I say wrong things or things that are not completely precise. And if they are recorded, then maybe you listen to them and then you think that they are correct because I have said that, but maybe they are not. So I don't know. I can do that, but it's a little bit risky. So I'll think about that. So. Well, okay, so I'll think about this thing, and if there are no questions and anything, so I'll just terminate this this seminar, this meeting, and wish you a good weekend. So I'll close here. Okay, so this is just the chat, close, and